Hi, we're Team 3. We're the, we're the slicing and palletizing team. So our subsystem involves, basically we switched from the egg slicing method, to this pushing method where the bricks come out on the roller onto this sheet metal, and then they're pushed with this pushing arm through the slicing wires here, so they're pushed laterally now. And with this design, some of the variables that we've been working to confirm are like the dimensions of the table, how many slicing wires we want, and then the force on the pushing arm, that sort of thing.
So like Emily said, we switched our design from a method that cuts from the top down to now one that pushes it horizontally. We have 8 wires to create 8 bricks, so this is your final cut that dimensions the large slab of clay. We switched designs because ultimately last time we talked about having some sort of foot mechanism that will leverage the slicer down from the egg slicer method. But really all we were doing there is designing something that was like this method with the lever arm. So we figured why recreate the wheel and create something new when we know this already works for a lot of other designs.
So one of the key parts, I guess, for after our subsystems, how do we get all of the cut bricks into a kiln to dry? And so we devised this rack cart, kind of based off like what you see in a restaurant or in a bakery. And they're really efficient, which is nice. However, we had a couple snags when we were designing this, so we need a few things clarified, such as how large is the kiln, or if that's kind of, will be built to kind of what we give you, or will that be built and then we'll kind of have that, or those dimensions known to us. Another thing that we were wondering is, what were the temperatures of the kiln? Is it just purely like a wood fire to help dry the bricks, or will it be actually a very, very hot clay firing kiln to actually increase the strength of the brick? Because that's too hot for steel, and it'll get about lemon yellow, and with the weight of all of the clay bricks on there, it will very likely sag and fail, slightly catastrophically. So those are questions that we'll kind of need to find out some answers to. And then the other thing is, do you want the cart to even be something where you can stack them on like a rack system and move a large quantity of carts over and then have them in the kiln and then take them out? Or would it be better to just move the bricks just on like a normal sized tray, just like kind of one level at a time? And then maybe stack them in a kiln to be fired. So those are sort of our considerations with the cart, but this is a concept we came up with for if you wanted a more maybe efficient rack system, load it up with bricks, move it into the kiln, and then you could have a couple of these racks which you could just kind of quick change in and out of the kiln as they need to be dried.
And just to clarify real quick, the racks that are going to be, or the trays that are going onto the cart are going to be able to sit right here. So we'll push the bricks right out onto it. The work will grab the tray and throw it onto the cart. So for our engineering analysis, basically we did a kinematic sketch, and we needed to find out the force of cutting the clay. So we took a piece of clay, put it on a scale, zeroed the scale, and then just cut through it with a wire, and it gave us like an average cutting force per inch of wire. And then we ended up doubling that value just because we weren't sure how dry the bricks were going to be when they're coming out of the extruder, and we just had like regular potter's clay. So we ended up with a 94.5 or 94.6 pound cutting force for all the wires. And then we also had to find the friction force between the clay and the table, because that was also going to be put into the pushing force required. So we found a kind of a general friction force of 0.6, which is based on some different dirts on steel. And so then adding that all together, the total force required at the pusher is 150 pounds force. But then the force that's required at the handle is going to be less because of the mechanical advantage. So doing some math there, we ended up with or it actually ended up being around 82 pounds of pushing force. The client driver personally thought that was actually pretty doable force since you had like your bike and everything you push with. So we took those numbers and ran FEA on them. The main parts were this linkage here, and then the lever arm, and then this handle, and the handle up here. And we ended up changing a few of the tube wall thicknesses and sizes so that our minimum factor of safety is 3.9 on any of the stress parts. I think this one was like around 15, and this was, the handle was around 4, and the extender was, I can't read it there, but it was higher than that. So we made them thick enough just based on like plain carbon steel, which would be like highly available anyway. And so for our FMEA, the highest risk priority components were the wires, the wire tensioner, and the bolts. And for the wires, we just chose the 1/16 wires again, like the other group did as well. And it has like 150 pounds tensile strength, and each brick is only going to be pushing like 10 pounds on the wire, so it has like pretty high factor of safety. The wire tensioners could also break, so we're going to be looking on buying those just off-the-shelf parts and make sure that they have at least a high enough tensile strength. If the bolts failed, which are holding all these linkages together, those are like could pose a pretty big hazard, because the worker could fall forward and get injured on any of the parts if they broke apart. So with a 1/2-inch bolt, since the bolts are pretty cheap, going down in size isn't really necessary, and a 1/2-inch bolt is going to have like a super high factor of safety, so that should never fail. I think the shear strength on them was around 30,000 psi, and we shouldn't see it even more than like 500 psi, so should be fine there. Yeah, we had to run FEA on this. So. Any questions?
How is your pusher table staying on the table? Or the pusher staying on the table? It looks almost like the force is being applied upward almost.
So you have the weight of this steel tube, but you can kind of see it right here. So essentially, if this is like a side view of the table, this will have a piece that kind of wraps around the table, so that'll also hold it square. And along with keeping it square, we plan to move forward with adding a little kind of like a guide right here, just to make sure we're cutting parallel. Go back to your question, where this piece that wraps under won't allow it to rise up.
And we were also thinking about adding like a little wheel on here, so like there would be a flat piece that comes down and has a wheel that would run on the bottom of the table. That way it just doesn't have any friction.
So maybe it's a question for you or previous team. So how much waste are we going to have per?
Right now, I think we told the team to cut it at 36 inches, which would leave, or 34 inches. So right now we have additional space on each side. So where it's coming out on the sides will be essentially waste that you can just pick up and toss it back into the hopper. So we'll be cutting
So like
about,
waste is
About an inch on each side.
Yeah.
1 inch on each
Yeah.
side.
So it'll be 32 inches of bricks that get cut into 8 different bricks, and then you'll have an inch on both sides that gets tossed back in.
Okay. So maybe you can have some sort of mechanism to collect those waste.
Yeah, we can look into
Because
that.
it's every time you have some, you don't want to just keep them. Any other questions? Okay, thank you.